All right, guys, welcome to Math Analysis for April 15th. Today, we are going to be talking about how to identify points where there is no change or a slope of zero. We began talking about this yesterday in class, talking about it in the theoretical, but now we're actually going to see it kind of hands-on. So what I have here is a couple of equations that we are going to try to identify a coordinate at which the slope is zero, or a point, an x value specifically. Now we said that yesterday, we said yesterday that this is really exemplified by a spot where the line is going from increasing to decreasing or vice versa, a point where the line is changing direction. So first off, we have just a pretty standard polynomial here, and we notice that this point right at the bottom, right about there, is where it changes direction. That actually, where I have highlighted, is specifically the exact spot it changes the direction at negative 1.5. So this is the kind of equation where if we were to find a derivative of this, x squared plus 3x minus 5, the one that's highlighted here on the left of your screen, negative 1.5 for an x value, if we were to plug that into our derivative, we would get a slope of 0. Now to show this off a little bit, I'm going to actually find the derivative of this equation. So I'm going to go step by step using our kind of derivative methods. The derivative of x squared is going to be 2x to the first, and then the derivative of 3x is just going to be 3, and then the derivative of negative 5 turns into 0 since there's no variable with it. That just goes away. So the derivative of this equation is 2x plus 3. So if we looked at this point where it seems that this line is changing direction at negative 1.5 here, and we plugged that in, well, 2 times negative 1.5 is going to be negative 3, and negative 3 plus 3 is 0. So that goes to show exactly what I was mentioning a bit ago, that this coordinate, where it changes direction at the very base of the parabola or at the top of the parabola or whatever the function it is looks like, is a point that is not changing, that is not moving, for lack of a better term. Okay, so we're going to take a look at some of these other coordinates as well, or not coordinates, but these other equations. So x to the third plus 5x squared. So we can see this equation, let me make it a little more bold, turns at a couple different spots. Every time an equation changes direction, or every time a function or a line changes direction, it's going to have one of those points where the slope of that point is 0, where it's not changing. So we see right here, the very height of this, what I believe is probably negative 3.33 or negative 3 1/3 is a point where it doesn't change. And then right here at 0, 0 is a point that it doesn't change. So both of these coordinates, both of these x values, negative 3 1/3 and 0, should lead us to a slope that is 0 when plugged into our derivative. Again, if we want to see that, let me erase what I have. And the derivative of x to the third is 3x squared. And the derivative of 5x squared is going to be 10x to the first. So if we were to plug in negative 3 1/3, well, I'd have to do a few more calculations there, I guess. Thinking of what's negative 3 1/3 squared is a little beyond my ability without a calculator on hand here. But suffice to say, we would get 0 if you plug that in. If you're sitting at home right now and you have a calculator in front of you and you want to plug in negative 3 1/3 to this into this equation, you should get 0. But if we plug in 0, then absolutely we get a slope of 0, right? Like 0 squared is 0, 3 times 0 is still 0, and 10 times 0 is 0. So we find out that both these points are coordinates that are not in motion or not changing in terms of slope. Okay, we're going to go through our last two, and we're probably not going to do the actual calculations with them. But let's take a look at this one. 3x to the third plus 4x. Well, we don't actually see a whole lot here, so we may need to zoom out. But even when we zoom out, let's take a look at this line. Does it look like this line ever changes direction? Because the thing is, it doesn't. This line never has that moment of going down to going up or vice versa. We just end up with a line that is constantly increasing. So this function, 3x to the third plus 4x, that I have written right here, is an equation or a function that does not have any points that are not changing. So there's no value of x that you could plug into this equation to get a slope of 0. Finally, I'm going to take a look at one of the problems from your actual packet. The very top one here is question number 21. And I'm graphing that, and when you see this, you're like, oh goodness, there's a lot of lines, but where's it changing direction? Well, sometimes we have these equations that are going to have big crazy graphs, and we got to zoom out a little bit. So I'm going to zoom out here, and whenever I zoom out, I notice, you know, up around here, it looks like that's changing a direction somewhere up there. So I'm going to zoom in a little bit to the top of this curve, and if we notice right there, that is the spot where it changes direction. -3 and 203. If we were to find the derivative of this, -3 would get us a 0. Now, we're also going to zoom out and go down because it looks like this thing has to have another point down there because it's going down here and it's going up next to it. So down here somewhere, it's got to go the other direction. And if we zoom out enough, we find out right there, that's a point where it turns around as well, at 6. So at the x coordinates of -3 and 6, at least I believe it was -3 we were looking at a minute ago, at these two coordinates is where it turns. This is one way to be able to identify where graphs have points that are not changing, by graphing it and just taking a look at this and identifying these coordinates. You can do this on Desmos on your own computer, and there's even a Desmos app for your phone if you would like to try that out there. This, however, is not the only way for us to find these non-changing x values. What we're going to be talking about in tomorrow's video is how to find the x values that do not change without having to graph, by working on that mathematically. So, if you have any questions about looking at this as a graph, feel free to email me. Let me know. I'll get back to you. Otherwise, I'll see you guys tomorrow, and we'll work on an extended version of what we're doing today.